Hello, welcome to my presentation of the results of my publication SKATES, the Interoperable Multi-Connectivity Communication Module for Reliable Search and Rescue Robot Operation. My name is Johannes Güldenring and I'm of the Communication Networks Institute of the TU Dortmund University. Today I'm going to talk about the following topics. I will start with the short motivation and the challenges of reliable rescue robotics. I will introduce to you SKATES, the Interoperable Multi-Connectivity Communication Module. And first of all, I will tell you how we structured the data link and the configuration. We will introduce how we transparently forward data and the protocol extensions we conducted. Afterwards, we are going to evaluate SKATES in a challenging environment. Finally, we will summarize everything and provide a short outlook. First of all, let's start with robots in emergency response. So typical emergency scenarios are where we have major incidents and areas which are difficult to access or dangerous locations. Sometimes the communication infrastructure is damaged and or destroyed and we cannot use it. In those scenarios, it's always same. We want to first thing we want to do is to create some situational awareness. We want to discover an area. We want to find missing persons or objects, and of course, in the end, fight the dangers or rescue the missing persons. In the end, we also need to coordinate other rescue forces. So I brought two examples here of those scenarios. The first one is the Notre Dame, the burning which took place last year, where the church burned. There were also some rescue robots involved in scouting the inner of the church because it was inaccessible and too dangerous to access the building. And the bottom one there's an image of some first-person view of an UAV, which took place during some flooding event, where a large area was flooded, and there was an investigation if there were some parts or missing people. So in those scenarios, it's very easy or close at hand to use some remotely controlled robotics. But every time we use those robots, we also face some challenges here, and this is most of the time the communication, because it's very challenging in some extent to enable reliable and robust communication. So let's have a look at those scenarios. So the main task is to control a robot remotely through exploration or search and rescue scenario. Off the left side, we have some remote operation control center. We have only some monitors, screens, control panels to steer the robot. We want to be safe. We don't want to go inside some burning. We want to discover, and on the other hand, we have the robot which is completely remote and driving around. So what we want to achieve is that we have very reliable connectivity at all times. So we want to communicate with our robot at all times. At no time we want to lose the connection. We need to control the robot. We want to see what's happening in there, and we need therefore extreme reliability. On the other side, we need very high performance. We also need some high data rates. We have a lot of camera material which needs to be transferred from the robot to make high resolution images. In addition, for the steering of the robot, we need low latencies. All in all, it's also mandatory or requirement that we have existing robots or control solutions. These are sometimes very old or proprietary protocols. We do not always have access to the interfaces of the robot itself. But these protocols need to be empowered to be more reliable and provide a higher performance. So this is where our solution approach, SKATES, come into play. We want to use multiple communication technologies and thereby create interoperable and reliable communication. So let's have a look at our different puzzle pieces of our solution approach. And the first idea is that we want to use multi-connectivity to increase the reliability. So again, we have on the left side our operator, on the right side our robot, and we want to use in the middle multiple communication links. Here in blue we have, for example, public LTE, we have Wi-Fi, which is also very common to use. And there are also other technologies, for example, proprietary mesh communication and so on. Yeah. So we have two parts of our solution. The first one is the back-end solution, which is at the operator. We have one uplink into the internet here. We have modem for proprietary communication, also the one access point for the Wi-Fi. And on the other side, we have the interoperable communication module, which is directly attached to the robot, which also has some modems for accessing the communication links. Yeah. For the implementation of the multi-connectivity, we used multipath TCP, which is an extension to the TCP protocol, and it allows us to use all interfaces for this communication and now increase this reliability on top of that. We had a lot of issues when we wanted to implement that, and there were two major issues. The first one is a net address translation, or also called NAT, which makes it very difficult to access the robot if you're using public LTE, for example. So because you do not get a public IP but a private one, so it's the operator is not able to directly access the robot. In addition, we also had issues with firewalls, which also blocked some parts. Therefore, we provide solution in form of an VPN, which is also where we tunnel all our data through, and hereby we enable that each data point is can be seen from each side, and it works very smoothly. We used open source protocol WireGuard for this VPN implementation. Another thing is that we want to enable all robots, all existing robots which we had, to use this multi-connectivity approach. If you have some proprietary solution which is directly built into the robot, we do not have access to its protocol. It's very difficult. So our solution approach here is to use some SOCKS 5 proxy. We used shadow SOCKS implementation here to tunnel all data which comes from the robot or from the operator over multipath TCP. Hereby we extended the shadow SOCKS implementation to make use of multiple interfaces to connect to. We fed those open source implementation back. You can have a look at it if you want. And yeah, so the shadow SOCKS proxy now takes all proprietary protocols which exist before, transparently proxies them over multipath TCP, and it looks like, I can give you also one example how it looks like. For example, a camera stream which uses the RTMP, the real-time messaging protocol. First, it uses we do not, for example, have a camera which uses protocol, but we are unable to change or modify it. It uses just plain TCP, but we need to upgrade it to use multipath TCP. So it would connect now to our SKATES proxy. The SKATES proxy translates this data stream over the SOCKS 5 protocol, which now uses also multipath TCP, and it uses at first only Wi-Fi or LTE, and if the connection bandwidth is not enough or the channel quality is not good enough, we can also take more links into account, like LTE, for example. At the back end now, the SKATES proxy now transfers this data link now back to a usual TCP, and the operator does not really feel like there are multiple links. He just sees there's this usual TCP stream coming out. So here's the hardware implementation which we used for the evaluation later. It allows a very decoupling of the communication system and the robot itself. So we have at the left side some Ethernet ports where we just can plug and play and put in the robot system. We have several space for modules, for example 4G modem or LTE modem, Wi-Fi modem, Wi-Fi 6 already is included here, and it's very powerful. So very modular. We can quickly change technologies, mini PCI Express, so we can just plug and play different technologies here if you have different needs, and just also attach it to other robots. Another very important part of our solution is that we implemented some real-time monitoring of all communication links. We have each communication link individually measured, and also the multi-connectivity approach here illustrated in orange as the multi-link. Also we have some Gorczak which shows the current throughput or current latency. We have the signal quality, which we also will see later, and we have some time series so we can detect bottlenecks or see if the connection quality may not be sufficient to operate the robot further into the same direction. It's very important when we're doing remote operation of robotics. So let's come to the evaluation part of our publication here and results. This is a robot which we took, which we created our results with. It's a wheel-driven robot. It weighs 60 kilos, so it's very heavy. It's very robust. It can go at different locations very easily. And we have included several camera systems on top of that. We have one 360-degree camera on the top. It has 6 individual cameras, but stitches them together to a unified 8K high resolution camera stream. You can look in every direction in the end. We have also some thermal imaging system. We have FPV camera, which is for the first person view of the operator. And of course we have our SKATES module, which is equipped with Wi-Fi and LTE antennas. We took this, we conducted this experiment as during this lockdown due to COVID, where there were no people at the university. The operator has been at his home office, so he really steered this robot remotely. And you see here a picture of the building, and in red is the trajectory where we have driven. We have the starting position, the bottom right area. We used Wi-Fi to Wi-Fi access points, which were in the area of the starting position, and the LTE was located roughly 800 meters away from the building. Here we have in the beginning here some corridor with very good Wi-Fi coverage. Then we drive through the stairwell area. There's a lot of concrete walls and pillars, and it has a lot of shadowing, and it's very difficult to drive through this area here. And of course we have a third area where there is no Wi-Fi coverage, so there we need to switch from the Wi-Fi which we have in the beginning to the LTE. For illustration I brought some video. If you want to watch it in full detail, there's a QR code in the bottom right, so you can watch it later. It's played in 4 times this real speed, so you see how we move along the building and see the environment. In the top you see the 360-degree view, and the bottom you see on the right side the operator perspective. On the bottom left the throughput over time. Let's have a look at the results and numbers here. On the first plot there is signal quality evaluated over the time. We have for LTE the SINR, the signal to interference plus noise, as one channel quality indicator. For Wi-Fi quality we got 1% of the Wi-Fi modem reported, and we see at the first that we had good Wi-Fi quality and LTE quality, but then we went to the stairwell area where we had interferences shadowing. The Wi-Fi quality vanished, goes down to 0%, sometimes it comes back up, but afterwards we go to the second corridor where we do not have any Wi-Fi coverage, and in the end when we drive back we have again some coverage. So how does the throughput of the experiment look like? So we have in blue again LTE and orange is Wi-Fi. So we have our video stream, which is roughly 12 to 14 megabit per second depending on the encoding. And here for the first part, for the first corridor, we were able to transmit all data over the Wi-Fi network, and then we went to the stable area, we had shadowing, and then we see the benefits of using this multi-connectivity approach. The signal strength of Wi-Fi vanishes and the multipath TCP takes over and transparently moves all traffic to the LTE. You do not see that on the video stream. It just runs smoothly. The Wi-Fi comes back a little bit, and the data rates also are transferred over Wi-Fi again, but afterwards there's no more Wi-Fi and we are transmitted over LTE. In the end, here he does not recognize the Wi-Fi as being full there, and to transmit it nearly equally over both links. For the round-trip times, as a third key performance indicator, we see that the Wi-Fi has very low latencies. We have approximately 5 milliseconds round-trip time, RTT, and for the LTE it was 50 to 70 milliseconds. But we see in the stairwell area we had, where the Wi-Fi signal strength decreases, we had a lot of packet losses, so where no round-trip time was measured, and also the round-trip time increased there. So let me summarize the achievements of my publication here. We introduced SKATES, the interoperable communication module for reliable and transparent data transfers in rescue robotics and search and rescue scenarios. We implemented SKATES on a robot system and also in the back end. We evaluated it in experimental validation in an empty building. This underlined the good feasibility of our solution here. And we are currently conducting more sophisticated field trials where we also go even further, not staying in this lost building, but go out really on fields where we have some very interesting experiments ongoing. But this is for the next year's WiMob, I think. So if you're interested in our work, have a look at the DRZ, the Deutsches Rettungsrobotikzentrum. And thank you a lot for your attention.